Oh, okay.
Enabling microphone. Now it's okay.
There are some central questions for this in this Erdos-Renyi graph. So, for example, we can think about the number of triangles inside the graph. So that's a random number because graph is random. So one can ask, for example, does the central limit theorem hold, or do we have a large deviation principle for this? So I'll talk about this second question, large deviations, in this talk, but I'll briefly mention first about the central limit theorem. So what is the central limit theorem? So it says that if we are given IID, so independent random variables, then, so I assume that for a moment that each has mean 0. Then if we take the summation of xi's and if we divide this by square root of n, then it should behave like Gaussian distribution. So yeah, if we take this normalization, then we have the Gaussian distribution. And so this is some kind of linear function. So if you take a linear sum of xi's, then we have the Gaussian behavior. And it is also known that if you take a polynomial instead of linear function, then we should expect some kind of similar behavior. So instead of taking this normalization square root of n, so instead if you're taking some suitable normalization of this polynomial, then we should expect that we see some kind of Gaussian behavior. Yeah. And now I'll talk about the large division. So what is the large division? So it is about the sharp asymptotic property of the rare events or atypical events. So by law of large numbers, so if we have n many random variables, IID random variables with mean 0, then law of large numbers says that average looks like 0. So average converges to 0. And large deviation theory is about what is the probability that average is not equal to 0. So for example, what is a property that average is equal to some average is close to non-zero number graph? And this quantity is exactly the number of triangles, right? So this is of course nonlinear function. So one can ask about the large division. So what is the asymptotic property that this number of triangle has some kind of atypical number of triangles? And it turns out that unlike the central limit theorem, this is indeed very hard problem. So this is posed by Janson and Ruciński in the paper Infamous Upper Tail. And after this publication, lots of people worked on the large division problem for this number of triangles. Okay. Yeah, so like this. So what's the property that number of triangle is greater than 1 plus delta times expectation? So this is very small number. So one can ask, what is the asymptotic property of this, right? And also the next question is conditioned on this behavior. So what conditioned on? There are some excess number of triangles. How are the edges distributed? So in other words, what is the most optimal way to have excess number of triangles? So we can think about two possible scenarios. So the first scenario is that we can enhance the edge densities simultaneously, right? So we can enhance from P to Q, right? And second possible way is, so in the original Erdos-Renyi graph GNP, so we don't enhance everything. Instead, we plant a particular subgraph, like click or hub. So these two are quite different. So in the sense that if you look at this first condition, so if you look at the first condition, this says that the optimal way to have excess number of triangles is, so condition behavior looks like homogeneous random graph, and second says that the condition behavior looks like inhomogeneous random graph, right?
I'm sorry, what is meaning of planted subgraph? I mean,
oh, so plant means that.
Edges or?
Sir?
I didn't understand.
Oh, plant means that we put a particular subgraph inside the edges, right?
So you mean adding edges?
Yeah, like that. Yeah. And it turns out that answer highly depends on the value of P and delta, as I will show you later. So in order to explain this, I will briefly mention the notion of graphene. So graphene is some kind of continuum version of graph. So what is that? So it is the symmetric function from 0 and square root of 0, 1. So f of x, what is f of xy? So f of xy can be regarded as a probability to put an edge between two vertices x and y. So you can regard any number between 0 and 1 as a continuum notion of vertex. And f of xy is exactly the property that we put an edge between them, x and y. And there is a well-known topology which is called the cut metric on this space. And I will not mention this now, but yeah. So this is quite useful metric to study the graphene space. And it turns out that this notion of graphene is very useful to study the large deviation of the triangle inside the GNP when P is fixed. So why is this useful? So let's focus on the Erdos-Renyi graph with edge density P. And one can easily see that this Erdos-Renyi graph converges to the constant function P. So this can be regarded as a law of large numbers in the graphene version, right? So it is quite obvious. So since we are putting an edge with property P, so this is quite obvious. And now one can think about the large deviation. So large deviation means that, so as mentioned before, what is the asymptotic property of this atypical event? So for example, we can think about the event that graphene is far from being a constant function P. Then how does that event decay in N? Okay? So this is about the large deviation question. So it is known that large deviation shows like this. So n choose 2 is quite obvious because there are total dimension is n choose 2, right? So if you have m vertices, there are total n choose 2 many edges, right? So this is dimension. So this is normalization. And the important thing is that we understand what the explicit decay rate is. So decay rate is given by some kind of entropy function. So what is the entropy function? So entropy function is given by this. So IP of u. So what is that? So it is some kind of distance between two Bernoulli distributions. So we have Bernoulli u and Bernoulli p. So Bernoulli is a random variable which takes value 1 with property p and 0 with property 1 minus p. So it measures some kind of distance between them. So obviously if p is equal to u, then it's 0. And if p gets far from u, then it gets large, right? So this theorem by Chatterjee and Varada says that the large deviation decay rate function is explicitly given by this kind of entropy function. So this is the integral of the graphene with respect to the underlying edge density P. So this is quite obvious because this says that if graphene F gets far from the constant function P, then this of course increases and we have a faster decay rate. So this is quite intuitive, right? And using this large deviation result, one can deduce the large deviation for the number of triangles. Okay, so if we fix the edge density P, then what is the property that we have this amount of excess number of triangles? So it always decays exponentially fast. So this is dimension, right? N choose 2 is dimension. So what is the decay rate? Decay rate is given by the entropy function, right? So decay rate is given by entropy function. But what is the condition? Condition is that we should have this excess number of triangles. So this is exactly the continuum notion of triangles, right? So we have 3 vertices x, y, z, and this product is exactly the property that we have triangles, right? So this total number of triangle is greater than 1 plus delta times the expectation, right? So this large deviation probability can be reduced to solving this deviation problem, right? So we need to minimize the rate function given this condition. So this reduction is very nice. So we reduced this large deviation problem to this variation problem. But the bad thing is that it is very non-trivial to solve this variation problem. So why is this hard? So I can show you the example. Okay. So we need to minimize this rate function under this condition. And it is known that if p is very small, so if p is very close to 0, then there is some kind of very interesting phenomena. So there exists delta 1 and delta 2 such that if delta is very small or very large, then this minimizer should be constant function. But if delta is middle range, then the minimizer is non-constant function. And it is also known that if P is quite large, then minimizer is always constant function regardless of delta. So this kind of variation problem has very non-trivial behavior. And it is a big open problem to solve this variation problem for general subgraph counts. So for example, if you think about, for example, bipartite graph, then how to solve this? Nobody knows.
Sorry, so just to double check, I'm following you.
Yeah.
So if we remove the conditions, so
Which
then-
condition you mean?
So the conditioning that you like,
Okay.
the triangle conditions, the minimizer is just
Constant.
constant P function.
Right, exactly. Yeah.
Oh, what does very small here mean?
Oh, yeah,
P
there
is
is
a constant, right?
there is a precise notion of smallness. So if P is less than some 0.2 like that, then there is some kind of phase transition. But if P is greater than 0.2 blah blah blah, then
Then it's always.
it is always constant.
Yeah.
Can you rewind to the Chatterjee Bardon theorem?
You mean?
Yeah.
Yeah.
That what is the rate function of f?
Oh, basically by integral of this or
Integral.
yeah over the
Integral of what?
integral. So f of xy is the some of the property that we
That's
put.
the graphon.
Yeah, f is graph. Yeah.
Okay. And
So this is some kind of average of the entropy distance over the whole scale.
oh, okay. So yeah, okay. Add rate function in there. Okay.
Sorry, so what is, so F is just something specific? Like
Oh yeah, f is any specific graphon. Yeah.
For any graphon, take a U.
Yeah.
So it doesn't have to be the limit of this.
Oh, limit is always constant function p, right?
Yeah.
So this theorem is not interesting when f is equal to p,
Okay.
because a large number says that it should look like constant function p, and this theorem is interesting when f is not equal to p. So if f is not equal to p, what is the decay rate? And decay rate is given by this entropy function. So yeah. So this result says that it is very non-trivial to solve the operative problem for the triangle cones. So its answer highly depends on the value of p and value of delta. And this kind of the form of non-constant function is not known. So nobody knows the explicit solution of this. It is just shown that minimizer cannot be constant function.
Do we know that this is continuous or not?
Not. I think nothing is known. Yeah, just non-constancy was shown. Yeah. Okay, so this is about the p fix, right? So why do you care about p fix? Because this kind of graph limit theory or graphon theory works when we always assume that p is fixed number, but this breaks down when p is varying in n. So what happens if p varies in n? Okay, so what happens if p goes to 0, for example? Then the previous graphon theory does not work, so it breaks down, so we need a completely new argument. And Chatterjee, separately Chatterjee and DeMarco Kahn showed that if p is strictly between 1 over n and n, they found the precise order. So p to the n squared p squared. So this notation says that this exponent is of order n squared p squared, so this is a constant times this. And this notation means that ratio goes to infinity. And after their work, lots of people tried to find the precise order of this. So what is the coefficient in front of this? So many people worked on this. And yeah, there are some lot. So there has been some works to find the precise coefficient here, under some restricted condition. So lots of people deduced this for a certain range of p. So p not in the whole range, p in the some kind of restricted range. But the breakthrough happened 3 years ago by Harel, Musa, Samochi. So they showed this identity for the whole range of p. So they verified this for whole range of p between 1 over n and 1. So this is quite breakthrough. So yeah, the argument is very different from the previous one, which used the Graphene theory. So they developed some kind of very new Gibbs measure theory to deduce this kind of large deviation result. So we understand what this means. So when P is constant, we discussed how to deduce this using Graphene theory. And if P is in the intermediate region, we know the result. But what happens if P is 1 over n? Okay. So what happens if P is of order 1 over n? And it is very easy to see that number of triangle converges weakly to Poisson. So for example, one can compute the moment of the number of triangles, and one can easily check that all moments match with the Poisson. So that's quite easy. And in particular, this weak convergence of the random variable means that for fixed number of k or bounded sequence of k, we have this decay. So this means that the property that number of triangle is greater than k is similar to the property that Poisson is greater than k, but it is known that Poisson tail distribution is exactly given by this, e power minus k log k. So this is the tail distribution of Poisson. Okay. But one can ask how fast this k must grow so that the Poisson approximation persists. So this weak convergence only proves the tail behavior for the bounded k, but one can check that, one can guess that if k grows very fast, then this approximation may not fall. Okay, so this is a quite famous question by David Erdos. And we work on this case, so P is 1 over n. So the constant D is not important. D can be any constant, positive constant. And we show that if k is below the threshold, so this means that if k does not go so fast to infinity, then the previous Poisson approximation is true. Okay, so this is still true. However, if k goes to infinity very fast, in this sense, if k goes to infinity very fast, then Poisson approximation breaks down, and the tail behavior gets very different. So it decays like n to the minus k to the 2/3. So there is some kind of phase transition at this point. K 1/3 log k is over log n. So yeah, in other words, Poisson approximation or Poisson behavior breaks down if k goes fast enough. So this is the precise growth rate. So I'll briefly mention what this means. So conditioned on the random graph having at least k triangles, so how are the edges distributed? So this means that what is the most optimal way to have k triangles? So what is the most optimal way? And we show that if k grows infinity slowly, then the most optimal way to have k triangle is just having vertex disjoint triangles. Okay, so disjoint triangles. That's the optimal way. Whereas if k grows very fast, then that cannot be optimal. Instead, we should have a clique of size k to 1/6. So and why do we have this size? The reason is that in the clique of this size there are k-metric triangles, right? And yes, and it turns out that this is indeed the best strategy to have k triangles if k goes very fast. So and in particular, this means that there are no other ways to have k triangles in an optimal way. Either this or this are optimal way. And in particular, so this result where we work on p equals 1 over n, and the Harambosa Samochi where they work on p greater than 1 over n and 1 between 1 over n and 1, and Cherish Varadan where they work p fixed. So these three regions completely settle the upper field problem for the triangle cost, so which was posed by Janson and Ruciński in 2002. And note that p less than 1 over n is not interesting, because if p is less than 1 over n, then the expected number goes to 0. So that's not the interest case. That's what it is. Okay, so this finishes the first part, and now I'll talk about the second part, which is the exponential random graph model. So I'll consider the Gibbs measure on the graph. So let's think about the collection of all graphs with n vertices. So what is the corresponding space? So it is 0, 1 to the n choose 2. So why? So because there are n choose too many edges, right? So dimension is n choose 2. And if edge is present, then we can put 1. And if edge is not present, then we can put 0. So there is very natural correspondence, right? And in the statistical mechanics terminology, any property measure on the space of configuration, on the configuration space, is called Gibbs measure. So if we have any property measure on this collection of graphs, that measure is called Gibbs measure in the statistical mechanics. And what is the Erdos-Renyi graph? So recall that Erdos-Renyi graph means that we put an edge with property P independently, right? So by independence, this is just product measure. Okay? And now I will define a non-product measure, which is called exponential random graph model. So we fix any graph G. So for example, you can regard G as a triangle. So we fix a triangle. Okay? And NG means that NG denotes the number of triangles inside the graph. Okay? So that's the object we discussed in part 1. And what is the natural Gibbs measure on the space of finite graphs? So we put this. So the property mass is proportional to exponential of the number of triangles. So this is the normalization factor. So you can ignore this for a moment. So this is just normalization. The important factor is this. So the probability mass is proportional to exponential to the number of triangles, right? So obviously, if beta is positive, then what is the highest mass? So highest mass is of course the complete graph, right? Because complete graph has the largest vector, right? And empty graph has the smallest mass. And in the statistical mechanics, the crucial object to study Gibbs measure is so-called the free energy. So what is a free energy? Free energy is 1 over dimension. So 1 over dimension times log of normalization. Okay? So this is a proportional factor, but in order to make this a property measure, total mass should be 1, right? So we need to put the normalization. And the free energy is 1 over dimension times log of this normalization. And it turns out that this quantity is very crucial to understand the Gibbs measure, so which I will describe later. So this is the example of ERGM. So we can think about the triangle, right? So this is the number of triangles. And of course, the probability mass, it gets higher when the graph contains more triangles, like this. And the completely different behavior happens when beta is negative. The opposite thing happens. Okay, so why is the free energy important? So before explaining this, I'll mention that the large deviation result that I mentioned in part 1 is very useful to study the free energy. So why is that useful? So what is the large deviation? Large deviation means that what is the asymptotic property of the rare event? So we learned that in many cases it decays exponentially fast, right? So it decays exponentially fast. Given this large division result, we can always study the free energy. So what is the free energy? Free energy is 1 over dimension. So here dimension is n. So 1 over dimension times log of the normalization, right? And this free energy can be written as supremum of Hamiltonian h minus the decay rate function in the large division. So you can easily check this. So yeah, roughly speaking, given the large deviation result, free energy is supremum of Hamiltonian minus decay rate function. But we know this result, right? So in the first part, I mentioned this theorem. So this is the large deviation result for the Erdos-Renyi graph. So if we are given this Erdos-Renyi graph GNP, we exactly know what the decay rate function is. So decay rate function is given by the average of entropy function, right? So we have a candidate for this I, right? So we have a candidate for this side. And H is, what is H? So H is the number of triangles, right? So in our case, this is number of triangles, and I is this entropy function, right? So one can apply this to our model. Okay? So we recall that we are studying this type of Gibbs measure, right? So it is e power, this is Hamiltonian, right? E power Hamiltonian. And using the previous thing I mentioned before, one can study the free energy, right? Free energy is supremum of the Hamiltonian, right? So this is the Hamiltonian minus the decay rate function of the large division, right? And we learned that we know what the decay rate function is. So this is given in terms of entropy function. And what is the Hamiltonian? So this looks complicated, but this is nothing other than the subgraph counting number in the continuum set. So if F is graphene, then what is the property that there exists a subgraph G? So we have this product, right? So this is quite obvious. So I'm just repeating the previous slide. Supremum of Hamiltonian minus rate function. But the non-trivial part of this result is that this maximization problem should always be obtained at the constant function. So you can ignore non-constant graph here. So graph this supremum should always be obtained at constant function. So you can reduce f equals u, right? So if you put f equals some constant u, then this is simplified to this very short thing, right? So this is the non-trivial part. So they show that. So we always beta positive. So if beta is negative, then this is not the case. So if beta is positive, then this supremum is always obtained at the constant function. So we just need to find the supremum of this simple function. So this is proved by Chatterjee and Diagonalist. And of course, and as I mentioned before, if beta is negative, then of course this first line is true, but second reduction is not true when beta is negative. Okay, so when we solve this, what do we get for answer? Okay, so we get this formula, right? So this is a free energy, and we say that beta is subcritical if this has a unique local maximum T. So there are some cases. So beta. So if you draw the graph, then for certain range of beta, it looks like this. So it has a unique local max. And for certain range of beta, it looks like this. Yeah, so it has two local max, right? And in general, for very small beta, it looks like this. And for large beta, the graph of that looks like this. Okay. So subcritical means that beta is small. Okay. Beta is small, so that graph looks like this. Okay. And what happens in the subcritical region? So it is known that subcritical ERGM looks like the product measure. So originally it is a Gibbs measure with very complicated Hamiltonian. So Hamiltonian is the number of triangle, right? So it is super complicated, but so these three people show that for any subcritical Gibbs measure, ERGM Gibbs measure, we have this. So what does this mean? This means that we put an edge with property P independently, right? So this is nothing other than Erdos-Renyi graph with P, right? So yes, we are in the good shape because even when we have very complicated Hamiltonian, one can say that, oh, the Gibbs measure looks like this Erdos-Renyi graph with H density P. But this is about the qualitative schema. So how the natural question is that, oh, how can we make this closeness property more quantitative? So this is just qualitative schema. So how much are they close, right? So that's very natural question. And in the property theory, the one important notion of closeness. So one useful notion of closeness is so-called the concentration measure. Okay. So what's the concentration measure? So it says that, so if we are given a series of random variables, the probability that any observable deviates from its mean by the amount t. Okay? So this means the deviation from the mean is t. Property of this deviation decays like e power minus t squared. So if we have this kind of deviation property, then we say that random variables satisfy Gaussian concentration. So why do we call Gaussian? The reason is that this decay rate is exactly the tail of Gaussian random variable. Okay, so Gaussian random variable decays like this. So I think you know this, but we have the Gaussian frequency. So this is roughly e power minus t squared. So this is the reason why we call this Gaussian concentration. And it is known that for independent random variables, this is always true. So if xi's are independent, then we always have this Gaussian concentration. However, this is very poorly understood for non-product measure. In particular, when measure is given by mean field. So ignore this. So what do I mean by mean field? Mean field means that interaction is some kind of long range. So yeah, right. So for example, if you think about the triangle counting, so it is the long range interaction, right? So for those kind of measure, it is in general very hard to check this Gaussian concentration. So in summary, for the product measure, it is obvious, but for non-product measure, it is non-trivial to check this. Okay, so the second part is about how to, so do we expect this kind of Gaussian concentration for subcritical ERGM? And we show that any subcritical ERGM satisfies the Gaussian concentration. And this is indeed the first Gaussian concentration result for very general mean field type case measure or the long range type interaction. And this has many applications. So for example, so this is one of the applications of this concentration. So why is the concentration useful? For example, when you want to prove the central limit theorem, Gaussian concentration can be used. So using this Gaussian concentration, one can prove the central limit theorem for the number of edges in the graph. So as I mentioned in the first slide of talk, so I mentioned the central limit theorem, right? And I mentioned that, yes, right? So in the central limit theorem, we have this. So this is called the Gaussian. And so so here the crucial condition is they are IID, independent. So independent is crucial. But for non-independent situation, proving this kind of statement is super hard. So in the case of independent thing, lots of things can be done. So this is very classical central limit theorem. And also one can put the polynomial here. So instead one can put polynomial, number of triangles. So this is number of triangles with some normalization converges to Gaussian. So this can also be proved. However, if underlying measure is not product measure, then even proving this is super hard. So even proving the central limit theorem for the linear function is very hard. But once we have some kind of Gaussian concentration, then one can prove the central limit theorem for this kind of linear function.
Can you remind me, what is a ERGM? Is this where you fix a subgraph and you're counting the number of copies of that, and then there's some...
Exactly, it's an exponential thing. Yeah.
So this is specifically for that type of exponential bound where you have a subgraph and the probability that a graph occurs depends only on the number of
subgraphs inside the graph.
Subgraphs of that type.
Exactly.
So, but for any subgraph, this is true?
Yeah, for any subgraph.
Okay.
Yeah, not only triangle. Yeah.
Okay.
Yeah.
Is the subcritical the high temperature regime?
Yeah, beta small. Yeah. Yeah.
Because I didn't see a minus sign.
Oh, but we only consider beta positive.
Oh, okay.
Yeah, for beta negative, this result may not be true. Yeah, I'm only considering beta positive.
So when you say subcritical, is it like small case?
Yeah, beta is small. Yeah.
Beta is small.
Yeah. But we only constrict to the case beta positive. So if you look at this, yeah. So first thing is that, so what's the bad thing is beta is negative. Then of course, as I mentioned before, this is not true. So one cannot reduce graphene to constant function case. So that's not the case when beta is negative. And second, what's the difficulty? So the second difficulty is that, so in terms of free energy, we expect very bad behavior when beta is negative. And second, in the probabilistic point of view, there is no correlation result. So if beta is positive, then there is always positive correlation. So correlation of two edges is always positive. So this is some kind of positive correlation. Positive correlation. So this is the case when beta is positive. But if beta becomes negative, then this kind of positive correlation property can break down. So this is also the second drawback when beta is negative. So in general statistical mechanics theory, when studying the Gibbs measure when beta negative is much harder than beta positive. Lots of the probabilistic tools breaks down when beta negative. Yeah, so we proved this for all subgroup beta. And how did we show this? So this is the last slide, so I'll briefly mention the idea of proof. So what is the difficulty? So as I mentioned before, the Gibbs measure does not exhibit any correlation decay. The reason is that the Hamiltonian is the number of triangles, right? So this is exactly the symmetry, right? So recalling the software counting, this is just symmetry. So there is no decay result, correlation decay. So instead of studying the decay, we studied the time version of this model. So we sample this Gibbs measure. So we think about the stochastic dynamics. So this is some kind of Markov chain on the graphs, on the space of graphs, and this is called the Glauber dynamics in the statistical mechanics. So it is quite famous model in the statistical mechanics. So if you think about this time version model, one can show that this Markov chain has a nice mixing property for any subgroup of beta. So one can show that if beta is small, then this dynamics has a very nice mixing property. So after a certain time, this Markov chain mixes very well. And one can show this, step one. And the next step is one can translate this temporal mixing property to the concentration property we mentioned before. And this is so-called the Stein's method in the property theory. So one can successfully translate this mixing property to the previously mentioned Gaussian concentration property. So that's quite technical result. So I will not mention that. But the key idea is that we don't consider the original model. Instead, we think about time version of this Gibbs measure. So that's the key. Yeah. So this finishes the talk. So thank you for your attention.
Thank you. Any questions?
So can you go back to the slide where you use some of the tools? Go back a bit more.
In
Or
this.
yes. Right.
Yeah.
So when you say free energy is equal to supremum over x.
Yeah.
So what is x?
Oh, so this is quite general thing. So this is the very general result which holds for any space.
So x is what you call like a configuration.
Yeah, like that. So yeah.
Then I mean in your result, your x became this function f.
Yeah, right. Graphene. Yeah.
So graphene is regarded as a configuration.
Yeah. So so there's some visible notation. So so this is originally.
So I thought
The-
configuration is like 0,
Yeah,
1, and then-
this varies in n, of course. So the dimension increases as n increases,
Uh-huh.
but the limiting space can be regarded as a graphene space.
Oh, okay.
Yeah. So we are on. Yeah. So also there is a non-trivial step to move from the discrete setting to this continuous setting. So there's after doing some technical work, then one can deduce that free energy is given by this.
Also, like, I mean, for somebody who doesn't like me, doesn't know about the use of free energy, so you mentioned about free energy is really important.
Uh-huh.
So why? Could you give me some
yeah.
like words about?
So free energy gives some kind of intuition about how the Gibbs measure looks like. So for example, if you analyze the free energy, so there are two terms in the free energy. So if you look at this variation problem, so there is a Hamiltonian which is called energy, and this is the rate function, decay rate function, which is called entropy, right? So there's a competition between them. So there's a competition. So this is called the energy entropy competition in the statistics mechanics. So what is the underlying measure? So underlying measure is just counting measure, right? So we count. What is the counting measure? Counting measure is p equals 1/2, right? Counting when we have Erdos-Renyi graph with p equals 1/2, then that's just counting measure, right? Uniform. So what happens if x is very large? So sorry, what happens if graph on f is very large? If f is large, then this term is also very huge, right? So this is this advantage, right? So f being large means that the configuration gets close to the complete graph, right? Then this has a huge mass, so this term, this term increases, right? But the disadvantage is that this minus term, this term also increases. So in the entropy point of view, the number of graphs which is close to complete graph, that's very small, right? So there is some kind of competition between this energy term and entropy term. And free energy, if you look at the formula of the free energy, one can find the explicit place where this variation problem is maximized. So that precise location explains some kind of intuitive behavior of the original Gibbs measure. So for example, if this is maximized at this p, then one can briefly say that, oh, this Gibbs measure looks like GMP. So in summary, if you can find the solution of the free energy, then that solution can give some kind of asymptotic behavior of the Gibbs measure. So that's the reason why free energy is important.
So this is for any. Is this specifically for these ERGMs, or is this more general for any? I'm trying to figure out what is this theorem.
Oh, this theorem is about this Gibbs measure. ERGM Gibbs measure.
Specifically about that case.
Yeah, but this kind of formulation is true for any type of Gibbs measure. So if you're thinking about any Hamiltonian H,
Yeah.
then this is always true for anyone.
This one is true.
For any Gibbs measure.
Yeah, the top
Yeah.
part is true for any Gibbs measure, but the one that's saying that it's maximized for f is only true when you're building your Gibbs measure based on in this symmetric way based on the subgraphs.
Yeah. So this is the specific result for
For
this.
that.
Yeah. ERGM.
How is there any relationship between this and the earlier result that you said, where you said there's for some range of p
I see in the triangle counts.
Yeah, for the
Ah.
triangle counts, where when the p is small, there's something complicated.
Of course, yeah, that's a good point. So there, of course, yeah, great. So there's a connection, yeah, right. So if p is small, then there is some kind of transition. Whereas p is large, for example, if p is greater than maybe 0.2, then yeah, always constant function.
Yeah.
So this is quite related. So if you go to this free energy formula, we show that this is always obtained at constant function, right?
Right.
But what is the p here? So this is a counting measure. So underlying measure is p equals 0.5, right? 1/2. And previously we know that for p equals 1/2, the solution is always constant function.
Yeah.
So that's compatible with this result. So in summary, studying the large deviation in the first part, and studying the Gibbs measure, so they are very related problem. So if we study the Gibbs measure, then that gives the intuition for the large deviation, and converse is also true. Yeah, they are quite related. Yeah.
So is there an example where the free energy is achieved by step functions, say, not constant functions?
So if beta is negative, yeah. So in that case, beta should be negative, yeah. But And it is known that if beta is negative, but if beta is very small negative number, so beta is small, negative number, but absolute value is, then this is still true. Yeah, for very small negative beta like this is still true. But if beta is large negative number, then of course it is known that this maximization cannot be attained at the constant function. But as far as I know, I think nothing is known about the precise form of the maximizer. So as far as I know, yeah. So the finding the answer to this variation formula is very hard problem, I think.
We have a question from the live chat, comment and question. So Jung Young Lee writes, I know the variational problem for bipartite graphs in the range of p being fixed depends on Sidorenko's conjecture. What is the smallest non-bipartite graph for which the problem is unsolved?
I see. So I think for D regular graph, something is known. For D regular graph, this kind of variation problem can be solved. Like triangle. Triangle is a particular two regular graph. So yeah. But for non-regular graph, I think almost nothing is known. Yeah.
I also have a question about the definition of exponential random graph model.
Yeah.
So in the exponent there's a term n to the v minus 2.
Yeah.
And that looks somewhat arbitrary. I mean, it could be, let's say for instance, if G has no edges, I was hoping that if G has no edges, maybe I want to have a uniform random graph, but
that's quite, that's very extreme case. So I'm showing that there's
still divided by n to the number of vertices minus 2.
So the reason why we take this normalization is that, so typically, so if G is not such extreme case, so typically this has n to the v, right? Typically. Of course, there are some exceptional cases, but typically, the number of subgraphs in this graph is n to v, right? And if we divide this by n to v minus 2, then this is of order n squared, right? But dimension is n choose 2, right? So in the statistical mechanics, we said this exponential has the same order as the dimension. So that's the reason why we take this normalization.
Okay. So the motivation is from statistical mechanics.
Exactly. Yeah. The order of exponent is same as the order of dimension. And in that case, this has some kind of non-trivial limit. So this is the correct normalization. So that this has some kind of interesting behavior.
Right. Any other question? Yeah, Tuana?
So instead of you consider that counting the number of triangles.
Yeah.
So maybe you consider that counting other subgraph rather than triangle.
Yeah.
So on the results today is hard to consider in that case.
So we are considering this for other than triangles, yeah.
Just different rather than triangle.
Yeah.
And so on the results today can apply in that problem.
Oh yeah. So you mean one can study this kind of free? You mean?
Yeah.
But yes. I see what you mean. So for general, but this is the case when p equals 1/2. So so maybe one can guess what happens when p is 1/2. But when p is other than 1/2, then it seems delicate to solve. Yes, to solve the previous variation problem. Yeah.
That also depends on P.
P. Yeah, it highly depends on p. Yeah.
Also, I have one more question. So, if I so here you normalize by and it's kind of weights by the number of subgraphs, like small picture G, right, or number of triangles.
Yeah.
What if we use some other functions, like let's say I take some function on graphs,
Yeah, that can that can possible.
and
Yeah,
like instead of number of
subgraph.
some triangle, maybe I take number of bipartite into subgraphs or whatever. Yeah, or that it could be just different things.
Yeah, of course, it can be anything, right?
Normalized by chromatic number, for instance.
Yeah.
And could that still give us something interesting, or is it like what kind of functions do provide?
So this motivation comes from the large deviation for the subgraph counts. So because they are quite related. So for example, if you're interested in the large deviation for the chromatic number, then yeah, you can interest this. Yeah, but I'm not sure. Yeah. But in the probability theory point of view, this function can be any function of the graph. Yeah. But whether beta positive or beta negative, that's crucial.
Are there physical models where beta is positive?
But physical model when beta is positive.
Yeah.
So what do you mean by that?
I mean, I'm trying to understand like what. Because usually we have beta negative, right? Or we have a minus beta. But
In the like easing model.
or just in general, like for Gibbs measures.
I see.
So
That's set up so that it has some kind of positive correlation.
yeah.
So this is compatible with that
Oh, okay. I see.
Yeah.
I see. You're just making it. I see.
positive correlation to it.
Okay.
Yeah.
Alright, any other questions? No. Well, if not, let's stop grilling him and then. Alright.